Okay, so thanks for coming today. I'm Mike Pilquist. I'm the current co-author of Functional Streams for Scala. I work at Comcast, where we do a bunch of cool Scala and FP stuff and do a bunch of stuff with video. Today, I want to talk about the FS2 0.10 release. And I want to do something a little bit different. Normally, when I give FS2 talks, I do a lot of evangelization of the library and show usage of it. Today I want to do that, but I also want to show some of the tricks we use internally to make it really fast. If you read the abstract, you saw that I claimed we had just released FS2 0.10. Unfortunately, I had to write that abstract back in the summer, and it was a little too optimistic. So 0.10 milestone 8 is available right now. We have a big ecosystem built on that milestone, and the 0.10 final release is coming really, really soon. Hopefully before the end of the year, depending on some other ecosystem stuff. There's three themes behind the 0.10 release. I wanted to simplify the API a bit, support the ecosystem, and improve performance. And so all the things I'll show you today will be sort of characterized by one of these themes. For folks that worked with Scala Z Stream, the transition from Scala Z Stream 0.8 to FS2 0.9 was a massive transition, right? It's a complete rewrite of the library. From 0.9 to 0.10, we had like 14 months of production use, all sorts of different companies using it, all sorts of different open source projects using it. And we were able to make some very small targeted changes to the surface API of the library. Not a full rewrite by any stretch of the imagination, but sort of sand off the rough edges. So let's talk about ecosystem. FS2, like things like cats, tends to be like towards the bottom of dependency graphs, right? It's this infrastructure-style dependency where you need a bunch of other projects to build on top of it to sort of make it useful for your business problems. This is a snapshot from the README for FS2 projects that are currently integrating with it in some way. You can see there's a bunch of type-level projects up here. Cersei's got some FS2 integration, Doobie, HTTP4S. I think as of right now, almost all of these projects have stable versions published for the 0.10 milestone 8 release. So don't be afraid of that milestone number. I have milestone 8 in production systems. It's really solid, but we need to wait for all of our dependencies to publish final versions before FS2 can be published. By the way, if you know of any other projects that are on this list, please open a pull request. Love to do it. You got one? Awesome. I definitely want to update this. We do have bindings for a lot of things. So maybe you're using Akka HTTP, but you still want to do FS2 style streaming for some reason. There's a project here that links the FS2 API to the Akka Streams API. And there's a bunch of other interop projects, including reactive streams. OK, I want to start with a sample problem to sort of give a feel for what it's like to write things in a streamy fashion. I figured we could do sort of first principle stuff, but I wanted to show something that's more unique to the FS2 API, things you don't necessarily see with other streaming libraries. So I had this example. This is more or less something that you might see in an app doing like Kafka integration or something like that. So we have this poll value. Poll is of type IO message. It's a program that, when evaluated, is going to give us a message from, let's say, like a Kafka topic, right? And we want to create a stream. And the stream, the general idea behind it is we want to go and poll Kafka every so often, maybe once an hour in this particular example. If we fail, like if we go to poll for a message and we get some type of runtime error, we want to do a retry. And we want the retry delay between attempts to have some exponential backoff, right? But if we succeed, then sort of store off the message we got. And then any point anyone wants to see what the latest retrieved message is, they should be able to pull on an element from the stream and sort of materialize that latest retrieved message. Okay? So we have like this continuous stream of always the latest retrieved message. And we want to do this in a way that we can preserve resource safety and overall compose this program into a bigger expression without violating referential transparency. So in order to do that, the first thing you'll see is the use of the scheduler type. So scheduler, we're going to say in the IO effect, allocate a thread pool of 2 threads for running tasks asynchronously. And the type that I get back from the scheduler.apply method is a stream of IO, scheduler. It's a stream because FS2 makes no assumptions on the effect type that it has any type of resource allocation or resource safety built in. FS2 builds resource safety on top of the effect types. And so in this particular case, we get a singleton stream. It's sort of an odd idea, right? If we're just allocating a scheduler, why do we get a stream of schedulers? But the idea is that we get a singleton stream back, we can flat map into that stream, and then generate a program that operates with the stream, such that when that inner stream, that inner program, finishes evaluation, then we know our scheduler is no longer needed, and we can shut it down gracefully, no matter how the program might terminate, right? And we'll see this pattern a lot in FS2. All resource safety is built into the stream algebra, so anytime you want to allocate a resource and then subsequently free it when we're done with it, it's going to be in a singleton stream structure. All right, once we have a scheduler, we might do something like this. Here we're using the retry method on the scheduler object. We say go off and run that poll program. Run the poll program, but if it fails, retry it initially at a 1 second delay, and then each subsequent retry, double the delay. Okay. Again, the type here is an I/O message, or stream of I/O message, and the reason it's in a stream again is that we've allocated a resource, right? We've registered some timer with the scheduler subsystem such that when this retry poll stream is finished executing, we want to unregister that, right? We want to unregister any pending retries. We then might do something like this to say, well, let's run the retry poll program, and when that finishes, we're going to append to it a sleep. So here we're using the scheduler.sleep operation. Again, we're saying sleep in the I/O effect for 1 hour. So this doesn't like block a thread or anything, right? This is like a semantic block, a semantic sleep. But in 1 hour, that stream will finish its effect, right? Finish its effect calculation, and then emit nothing. So the actual type of the expression on the right-hand side of the append is a stream of I/O comma nothing. And if I have a stream of an I/O message and I append to it a stream of I/O nothing, I end up with a stream of I/O message that sort of is, pulling an individual message and then, running the second stream just for its effect of waiting. Okay. Then we repeat the overall stream, and we do that an infinite number of times. Right? We just keep on running. And then finally, we get to this async package. So FS2 has an async package that's got a ton of different concurrent data structures and combinators built on top of them. Here we're using the hold option data structure or combinator. This combinator is sort of interesting. It takes a stream as a parameter, and it returns us a stream back. And when the return stream is pulled on, what it's going to do is run the parameter in the background, right? Go off and concurrently start executing repeat poll. And for each value that's pulled out of that stream, it's going to be written into a memory cell, like a mutable memory cell. That memory cell is wrapped in a data structure called a signal, which lets us register and look at the way in which it gets set in memory. And the net result that we get back from hold option, again, is another singleton stream. It's a singleton stream of a signal that then we can use to decide how we might want to read from the signal. In this case, we call that continuous method on the far right, which basically says anytime someone wants to ask for a value from the signal, just continuously give them whatever the current value is. Okay? It's hold option because if someone pulls from the signal before we've successfully pulled a single element from that concurrently running stream in the background, we get a none, and otherwise we start getting sums, right? And if the overall program, you can see stream type stream of IO option message, that overall program is only run for like the first 3 elements, and then they terminate, then all of these resources we've allocated are all sort of unwound in reverse order and shut down. Okay? So this is sort of the idea behind the FS2 API. We want all of this resource allocation and resource management in a way that preserves functional programming. The other thing to point out is that nothing here does anything. If you were to look at this latest message, you have to actually compile it down to an I/O program first via one of our run methods. That would give you, in this particular case, would give you like an I/O of option message, perhaps, or a bunch of other different options. And then eventually you'd have to go and evaluate that I/O program at the edge of your program to actually cause it to do stuff. So when I say like repeat poll is off running in the background with hold option, I really mean conceptually when the overall program is evaluated. Okay, so if you've used FS2 0.9, you noticed I'm using the I/O type here. This is the cat's effect I/O type. FS2 0.9, we didn't want a dependency on either cats or Scala Z. So we imported the Scala Z concurrent task data type and sort of cut off some of the rough edges, some of the unsafe operations that were there. I was talking to Daniel Spiewak about 6 months ago, and one of the things we talked about was pulling this task data type and sort of standardizing on an I/O type. He had some ideas on how to make task a lot better. And so we ended up with a CATS effect project, and FS2 moved wholesale to it. Right? So we actually deleted the fs2.task type completely out of the library. All of our examples now use the I/O type. But this is really important. I want to make sure this is clear. FS2 does not care what I/O type you use. Right? FS2, everything in the library is parametric in the effect type. As long as you can bring type class instances for the type class, for the effect type that you want to use, you're free to do so. And so, for example, Monix 3, if you want to use the Monix 3 task data type, it has all the type class instances necessary to do everything we just did in that last example, right out of the box. All right. In 0.9, we didn't want this dependency on CATS or Scala Z, right? And so we had this minimal type class hierarchy. So this is sort of like a library design dilemma here. We didn't want to produce a third functional programming library, but we also needed the abstractions that let us talk about building streams that were parametric over an effect type. And so we did this. We had like sort of the big four, right? Like the 99% of functional programming up here in the top left corner. And then we had these four others in the bottom right. And we really wanted these to be minimal. We only wanted the things that were essential to represent the programs we were trying to represent. So we didn't have things like the EQ type class. We didn't have things like semigroup and monoid. That became kind of obnoxious as we were trying to write the library, but becomes even more obnoxious for users, right? To go and use this with an individual library, you needed some type of shims library, and a bunch of things that we could have done in a sort of a more principled way. We were limited because we didn't want to, build this library up to be huge. So in 0.10, FS2 depends directly on CATS. We use the CATS type classes for these sort of top 5 now. Monad error is in CATS core. And then the bottom 4 come from the CATS effect project. If you study like the bottom 4 here versus the bottom 4 in the previous slide, they're sort of like rearranged, and like if you actually look at the operations, they're not quite the same thing. But again, as part of the work that went into CATS effect, Daniel Spiewak did a bunch of work taking feedback from like me and Alexandru from Monix and others, and sort of shifted around the functionality, and this is the type class hierarchy we ended up with. One of the things that's kind of interesting here is that in the 0.9 release, we needed this ability to do like these memory cells, these like mutable memory cells that we can allocate in a referentially transparent way. So they're sort of like these MVARs, right? We call them refs. In 0.9, we had a type class that talked about what it meant to create an MVAR. In 0.10, we do that as like a library function off of any old effect. So the important thing about that is that the ref implementation that you would need requires a bunch of infrastructure, right? It requires a bunch of infrastructure related to like the way in which concurrent operations execute. It's not trivial to implement that 0.9 type class. Here we don't need to, right? So we don't need like the Monix authors to write an FS2 compatible ref implementation. We can derive it directly from their effect instance. This is at least the second time this picture has been up on a slide this conference, right? This is Rob Norris' infographic. And this is just to say that like there's a lot of good stuff between all of the big type classes, right? We saw Rob talk about commutative monads earlier. There's all this other stuff that, by depending on CATS, FS2 can use as appropriate throughout the library, but also users benefit quite a bit from. OK. So here's another sort of, library design type dilemma. We published 0.9. I stood in this spot a year ago, extolling the features of 0.9. And a few months later, I was with a colleague, and I was doing a code review. And I saw this line, and I got confused, and I thought, surely this cannot compile. I wrote the evalmap function. This makes no sense. So what's evalmap? Evalmap is sort of like map, right? You map on like a functor. You expect to pass an argument from A to B, right? And on a stream, maybe like on a stream f of A, you'd map a function A to B and get back a stream of f of B. So evalmap is a little bit different. Here we're going to say, given an A, return an f of B. So on a stream of FA, we take a function from A to FB, not a stream of FB, right, but just an FB. And then we're going to sort of evaluate that effect and like lift it back into the stream type. Okay? So it's kind of like flat map, kind of like map, sort of like halfway between. So what are all these type parameters? Task, task, foo. That makes no sense, right? So looking at the 0.9 source code, it turns out in some type of fever dream, I implemented the FS2 version of Ken build from. We had this like this lub1 type, right? Which I don't know. So it's trying to say that like I don't know, the type constructor G, find the least upper bound between G and the effect type of the stream you're running it on, and compute that as like an output of lub here of lub1. This is like variance tricks to make one certain type of program compile. And so in 0.10, I'm really happy to say that eval map mostly looks like this, right? I know that's kind of low on the slide. Mostly, right? So this looks like this in 0.10. Literally, if you go look at the code, you'll see this. Now, unfortunately, we still have this little bit of variance nonsense to deal with. And it involves the fact that like if you try to eval map a pure stream, we want to be able to do that with an effectful type and then infer back like a stream of I/O whatever, right? So we sort of want to lift pure streams into effectful streams as an effect or as a derivative of eval mapping. And so in order to do that, you sort of have to, well, we either have to convince folks to fix a bunch of things as it relates to like nothing being inferred for type constructors in covariant data types, or we have a little bit of syntax trickery to do. So anyway, but the cool thing is if you look at eval map, this literally is the way it's written. There just happens to be another eval map a little bit further in the same file that looks a little bit differently. OK. So again, library design, lesson learned here. All of these things have good justifications, by the way, but when you kind of step away, you can see maybe we should do it differently. So here is an example where we gave users just like meaningless choice, right? This is silly. There's a bunch of different ways to do things. So filtering, right? We wanted to represent all of our really pure stream transformations as like standalone functions that are like universally quantified in like the effect type and whatever other input and output types they have. So in order to write that in Scala, we need to do that as like functions in an object or methods in an object. So we had this pipe object with methods like filter. Filter would be defined like completely, with no constraint on like the effect type. But then that's sort of obnoxious to work with. We don't want to have to like apply these pipes all over the place. So then we'd have things like source.filter. To make it worse, we had things like unknown terminate, which said like given a stream of f and an option of some type x, turn it into a stream of f and x, but when you hit a none, stop, right? You're done. Well, because the input type there's an option, like we didn't have syntax for that for some reason, right? And it's like why would, again, as a user, why would you have to know? Like why do you have to care? And then other weird things, like this concurrent object was an object that sat in the top level package. It had one function in it called join. Okay, I don't know. So in 0.10, these are all what you'd expect. They're just methods on stream. Okay. So we made some things simpler. So I'm going to make something much more complex now. So the sort of the trick of performance in any type of stream library is to move values through the stream pipeline in like batches, right? It's the easiest way to get performance through any type of stream library. And FS2 is no different. In 0.8 and prior, the collection type we used to move elements around was vector. And so when we started using it in production and started looking at the performance of that library, we're doing silly things like spending 20% CPU just creating singleton element vectors, right? Because we're creating these big 32-element arrays for all these singletons. So in 0.9, we introduced this chunk type. So the chunk type is a strict collection. It's finite. It has a size, and it has O of 1 index-based access, right? And then we had specialized implementations of chunk for things like singletons, for empty chunks, for chunks backed by arrays, chunks backed by vectors, including chunks backed by every primitive array type. Right? So you can move like big unboxed arrays of bytes through the stream pipeline without paying a per element cost. And this works really well, but like I said, I wanted to make it more complicated. So we added this segment type. So we introduced a super type called segment. And this is really like a stream library in a stream library. So this one's a pure stream, you can think of it. it can output 0 or more values of a type O, and then it finishes with exactly 1 value of a type R. Right? So it's got output values and it's got a result value. And this uncons chunk method is a good way to think about it. Like, given a segment, one of the things you can do to it is sort of destructure it. Like, say, give me the next bit of data in this segment. And you're either going to hit the end, in which case you get the result type R back, right or left, or you're destructuring like a head and tail, in which case you get a head represented as a chunk, right, as like a finite set of elements, and then another segment that you have to process. So why did we do this? And the key insight, it's actually one we even saw in the keynote this morning in terms of distributed computing, right? The key insight is that there's a whole bunch of work you do in between evaluating your effects. And the work that we do between those effects, we want to fuse together and fuse them in a way such that we're not doing intermediate value allocation, right? We knew this in 0.9. In 0.9, we supported map fusion. So you could map over chunks, and we wouldn't create like all of the intermediate chunks as we executed the stream pipeline. But we only did it for map. And it was specialized in the stream interpreter. So here, what we have with segment is that we can fuse arbitrary operations, as many as you'd like. We have full stack safety. We can do flat map. We can do zip width. So if you look at the literature around this stuff, like flat map and zip width are sort of the two like test cases that differentiate like fusion approaches. And the way we do it is through this technique called staging. And the general idea is that the staging technique we use, we want to take advantage of all of the intrinsics of the JVM, and we don't want to like build a code generator. We don't want to use macros. We don't want to use LMS. We want to do this in a way that's relatively easy to write. Okay. So the general idea behind staging is that given a segment, we're going to do things like map, map, filter, flat map. And we're going to get back now another segment, right? And now when we want to evaluate that segment and actually look at the output values and look at that result type, we're going to compile the segment down to a machine, like an imperative machine. We represent these machines as something called steps. And then we're going to like run those steps over and over and over and over until we hit our termination condition, typically that we've hit the result type, right? That R type. And just sit there in like a tight loop. And so I want to show you what this looks like. So here's segment. Now, I said this is this type is stack safe. So it turns out it's kind of hard to do that. So I want to delete some stuff right away because it's sort of obnoxious to talk about stack safety. So we've got like these depth and defer parameters, and it sort of obfuscates what this thing's about. We're also returning this eval type over here. That also obfuscates it. So we didn't have to worry about stack safety. It would basically look like this. What we have here is this stage operation on an abstract class called segment, and it takes 3 callbacks, right? These are mutable callbacks, right? Because this is like compiling us down to this imperative machine. We have a callback called emit that takes a single output element O, right, to unit. One called emits that takes a chunk of O to unit. Final callback called done, saying here's your final result type R to unit. And what you get back, had I deleted it right, is a step of OR. The step is the machine, the imperative thing. Okay. Let's look at something like toList. Right? toList, what we're going to do is say, forget about the result type. We don't care about it. We just want to run the segment and convert all the elements to a list. So here, we kind of have to jump around a bit, but we allocate like a big mutable list buffer and say, for each chunk C in this segment, go through and add all of the elements of that chunk into the segment. And if we look at for each chunk and bounce around a bit, we eventually get to code like this. We create some trampoline to handle some of the stack safety. We stage. There's our call to stage. We build the machine up. And then we basically sit here in a loop forever and just say, while true, run the machine. Like this is literally executing that machine. This particular evaluator actually uses non-local flow control through this done exception. So I apologize for showing that. But nonetheless, we can do things really fast with this approach. Let me give you a couple other examples real quick. Let's look at map. So map, right? Function O to O2, and we're going to give back a segment of O2 comma R. To implement map, what we're going to do is return a subtype of segment. The output type can be O2. And we're going to have to implement that stage operation. So again, just forget the depth and defer stuff. But we get a bunch of callbacks again. We get 3 callbacks. Now the output type is now O2. And so map can be implemented in terms of like staging the outer segment, right? So when we're staged, we're going to stage the outer segment. But when we do that, we have to pass callbacks to the outer segment. And so if you sort of follow the types through here, it ends up being pretty obvious how to implement it. Like the type system guides you to the right implementation in this case. In effect, what we have to do for the O callback, for the emit a single value callback, we're just going to apply the O value we get with the function f, or to the function f, and then emit it through our emit callback, right? If that makes sense. Here's how Fusion works. Here's how we avoid the intermediate allocation, this second one. We say if someone emits a chunk of O's, rather than like mapping that function over that chunk of O's to turn it into a chunk of O2's, which would be all this intermediate value, memory allocation, instead we're just going to sit there in an imperative loop, right? Rip through each individual index in the chunk and use the single emit callback. Okay. And anyway, when you implement enough of these combinators this way, including things like flat map and zip width, we're able to do this in a way where we can fuse anything, still keep the stack safety, and avoid those intermediate allocations. Now I said chunk is a subtype of segment. And so here's an interesting example. Chunk's a subtype of segment, but segment, all the callbacks take chunks as arguments. And then when we stage a chunk itself, like when we stage a chunk as a segment, we need to build up a machine that emits the chunk itself, right? So it sort of feels very circular. I was lost somewhere in there. So here's how it works. When a chunk is staged, we create a local mutable emitted state. Again, think of we're building an imperative machine. This is like a register in the machine, right? And we're setting it to false. We use the step constructor, and I want to look at this part right here, the highlighted part, lines like 29 down. We basically just say, like, when the machine is executed, when we get a chance to run a little bit, we're going to check to see if emitted is still false, and if it is still false, we're going to set it to true and then emit ourself out through our callback. Okay? And then regardless of whether we did that or not, we'll indicate we've reached the end. We're done. So this is great. We have all of the type complexity of FP and all of the bugs of imperative programming. There's also this really neat thing here. This is also sort of novel. You don't see this often with Fusion stuff. We want the ability to kind of come out of the machine, sort of like go from the compiled machine that after it's been executed for a little bit with all of these like registers that have been set to various values, and kind of lift that back into the pure immutable world. And we use this for like the take operator on segment, for example, where we can run take through like this big complex segment through all these fused operations. And then when we reach the end, we can say like, well, let's decompile or go back to the pure world, restoring some state, and we can return like the remainder of the segment post the take, right? So you can sort of imagine like a take being implemented such that it gives you the equivalent of like a split. Okay, so I hope I scared you enough with the internals there, or at least enough that you come find me later. Some other simplifications. This is a cool one. FS2 internally is nothing more than a big free algebra. It's just a big free program, right? So you can't get access to it. The algebra itself is inside the library. But in 0.9, we had 2 different algebras. We had one for streams and one for pools. And it's a very common operation to go from a pool to a stream when executing stuff. And so we had to translate those 2 algebras. Like every single time you went from that pool to stream, we had to do a translation step. And there's a runtime cost to doing that step. What we found is that they didn't really need to be different. Like this isn't like, we didn't make them the same by sort of taking the union of all of their operations. We sort of moved around the operations a bit and actually found that they are in fact the same. So this is really neat that a stream and a pool are 2 different like surface APIs for the same underlying construct. Now there's a catch. I'm really full of them today, aren't I? It's not a free algebra, it's a free C. So basically what we've done is taken a free mode and added this fail constructor. Again, I apologize at the bottom of the slide here. But in effect, we can suspend errors in our free construction, right? Because we can suspend errors, we have a way to observe them. We have this onError operation. OnError is sort of like flat map, but on the left side. Right? So it's a function that says from a throwable that may have been suspended, resume with some other free C structure. Okay? And then we do maybe controversial things like catch exceptions that are thrown from the pure functions. Like if, as we're computing the free C in flat map, if it throws an exception, we catch that and use the fail constructor. Right? So with this, which by the way is enough to implement like a synchronous I/O type, this alone, with this we're able to give all of the resource safety guarantees of FS2 using this algebra. This is it, right? So FS2 is like a pretty big API, right? There's like hundreds and hundreds of operations. The algebra is right now, well, this slide claims there's 8 items. That's mostly true. There's 10 because 2 more have been added thanks to a bug Rob found about 2 weeks ago. But there's really not much to the core internals, right? There's the output and run, which just basically let us get segments out of the stream. There's an eval step that lets us evaluate f of r's, right? Like some effectful value. We've got like 4 things for dealing with scopes and resource management, making sure things sort of unwind and get freed correctly. And then finally, we have this uncons async thing, which is unique to FS2 in that we can do asynchronous streaming operations while preserving the resource safety semantics. Right? No other streaming library does this in a functional way. And so uncons async kind of looks like a nasty type, but really it's taking a stream as a parameter. It says, I'm going to take a stream. This happens to be like the unnew typed stream, right? The wrapper is no longer around it. But take a stream S as a parameter and pull the next chunk from it or pull the next segment from it. Don't do it synchronously, though. Give us back sort of like a future, kind of. It's an async pull, right? And then I can do things like race to async pulls in a resource safe, completely 100% safe way. This is not racing to effects. This is racing to async pulls, which is totally safe. All right, so my last couple of minutes, I want to give an example of how this performance work materializes. I've got 4 different take implementations. And so if you've never used the library, often you'll go from a stream object to this pull object. It's a lower level API where you can then start literally pulling elements one by one. And so a common pattern is you might write functions like your own version of take in terms of this pull API. So typically these are recursive functions. Here this internal loop is a recursive function. Don't worry too much about exactly what this code's doing. It's basically just saying decrement n each time through by 1. And as long as we keep getting one element from the stream, keep recursing. Right? As soon as we're done, shut down the overall stream. So this is pretty intuitive once you get used to sort of the recursive API. The key line here is the else block. It says s.pull.uncons1. So on the stream, we're going to start pulling on it, and we're going to uncons a single element. Okay? Another way to implement this, we can uncons a chunk of elements at a time. Right? So again, all stream libraries want to batch their data as the data flows through the pipeline. So here we can sort of go down a layer and say, well, give us access to the batches, give us the chunks. So if we uncons a chunk at a time, our logic gets a little more complicated, right? Because now we got to account for like this case where we're taking 3 elements, we get a chunk of 10, right? So we got to, in that case, cut up the chunk. But more or less, it's relatively similar. And then finally, we have this even lower level API where now we can access the segment structure of the stream. Right? Remember, segments are sort of like a bunch of chunks that have been fused together in various ways through various operators. Again, I'm not going to go through the exact example here, but the general idea is we got a stateful fold, right, or a stateful scan of the segment structure of our stream, right? And we're saying for each segment that comes in, do some operation with it. In this case, we're using the take operation on the segment, and then depending on like whether we reach the end of the segment or whether there were more elements or whatever, we change the overall state in the scan. All right, so this is going to be a bit of an eye chart, so don't worry about the exact numbers. The takeaway is that 0.10 is much faster. Specifically, over in the fourth column, by the way, is the 0.9 native implementation of take. So specifically, if you do sort of the apples to oranges comparison, which is the chunk-based take in 0.10, the second column, with the 0.9 take, you can see it's about 4 to 5 times faster. The rows here represent streams with different chunk structures. So the first one is almost the worst example to use for the first row, the worst example you could possibly use for a streaming library, because we've got all of our data in one big array. So if we have all of our data in one big array, why are we streaming? Right? We should just use the array API. But if we did do that, you can see that the chunk version is still much faster. The element and the segment versions are significantly slower in 0.9, and I think it's the only case where 0.9 is still faster. Sort of on the opposite end is this stream unfold 1, the third row up from the bottom. This is the one that we all often will create accidentally when working with stream libraries, where we've gotten rid of all of our chunkiness, all of our batchness, right? And now we're pushing individual elements through the pipeline. On the right, you can see 0.9 was about 40K ops per second. Segment take is 162K, so again, about 4 times. Oh, I'm sorry, I was in the wrong row. Go up one. It's 1.4K ops per second versus 50 K ops per second, right? So there we're looking at a even bigger increase for the most common usage pattern of the library. Victor Klang recently posted this. He, performance tuning pro tip: optimize the bottleneck and repeat, right? And I think this is very true. But I think there's this corollary that we have to continue to remember when doing performance work, and that's that you have to know when to back up and try something completely different, right? Sometimes we get so focused when doing performance work of just optimizing the bottleneck that we never stop to think, well, maybe we're solving the wrong problem. And that's exactly where we were with 0.9. Like I was looking at, again, JVM level, intrinsics around how fast we can execute free. And Paul said, hey, why are we even doing that? We could run through the overall trampoline, 1/10 the amount of time. So that's all I have. 0.10 is much, much faster for anyone using it. We do have a full migration guide that does go through the full API and introduces the new stuff. It'd be remiss not to mention this paper. It's an awesome paper, Stream Fusion to Completeness. It's an Oleg paper. It's from this year, from 2017. And he implements a streaming API for pure streams, not effectful streams, but a streaming API in Scala using staging to get the performance of native imperative while loops. Now he does it with LMS, so his stuff will be significantly faster than FS2 segment. But if you can use LMS, the staging library, Oleg stuff can actually generate code that looks like it was hand optimized. And anyway, special thanks to Paul, who's done a lot of this work with me. And I think I have time for 1 or 2 questions. Oh. John's got to have something.
Looks great. Great work there. Thanks. I like the approach.
Cool. All right, well, thanks, everybody.